beautiful students. At first, wish you very happy Makar Sankranti. So I just wanted to tell you very much sorry that on 13th Jan I was about to come live, but I couldn't come because of some medical emergency. But today we are going to rock in this chapter solution. So please let me know, are you ready to proceed with it? So there was too many of questions like how we are going to conduct the session, if we can cover the entire second PUC chemistry and the KCET as well. So let me just tell you, my dear, just a little bit brief about it. Like, we will do the concept. Even if you have no idea about this particular chapter, that is solution, then also you can get to know about it, like from the very beginning, from the what is basically different type of solution, then thoroughly we will move towards Henry's law, Raoult's law, everything from starting to the KCET. Okay, I will make you the master of this subject, of this particular topic. So without further delay, let's start. And my one request to you people, that please share this particular session with at least 3 to 4 of your friends, so that they can also get the benefits of this particular session. Okay, I can see so many of you. Hello, my dear. Okay, so let's start with a little bit analysis of this particular chapter, both in KCET and in your board examination. So just let me tell you, my dear, in board examination, it is one of the highest weightage chapter, and overall marks you can get 12 from this particular solution chapter. Okay, and here you can see the number of question from different topic from the solution chapter. It came throughout the year. Okay, so here you can see from the concentration term 2025 one question came. Here from the ideal, non-ideal one question came. Here from the colligative property you can see last 5 years this is the target zone. So definitely we will also focus on this particular zone. From the colligative property, maximum number of question came in last few years. Okay, and here you can see this is for the KCET analysis. Here you can see 2025 5 question it came, 2024 5 question, 2023 3 questions, 22 5 questions again. So you can see the weightage of this chapter, and you can also understand how much important this chapter for you for the both KCET and PU2 examination. So yes, let's proceed a little bit. So here definitely first we are going to start a very basic thing, that is the type of the solution and what is solution. So like there can be different type of solution, like solid solution, liquid solution and gaseous solution. Yes, I can see so many of you are commenting. How are you? I'm absolutely fine, my dear. Whenever you people are joining and asking me, it's such a pleasure that yes, my students care for me. So yeah, let's proceed further. Solid solution, liquid solution and gaseous solution, and here you can see these are the example of it. Very rare possibility, but still you can get this type of question, like what type of like give one example of the solid solution. Okay, or in MCQ also you can get this type of question, that one example of the solid solutions are this options will be there. Okay, so someone is asking how long is the session. So my dear, if you really don't want me to proceed from the concept to the KCET level, if you don't want me to make you a master, then I can make the session end up till like it will take 30 minutes. But if you really want me to proceed like that, so that you can be a master of this particular subject in this only one session, it will take time better, maybe 2 hours, 3 hours. Like until you people will be satisfied, I will keep teaching you. Okay, so this is the answer of your question, my dear, how long the session is. Okay, hello my dear. Okay, let's proceed. So you can see gaseous solution, when it comes, the solvent must be gaseous. So whatever the solution I am taking, that must be in the solvent phase. Okay, so always remember the physical property of the solution. It should be reflected the property of the solvent itself. Okay, so here you can see mixture of oxygen and nitrogen gas. Chloroform mixed with nitrogen gas, this is liquid and gas. Next is solid and gas, that is camphor and the nitrogen gas. Okay, next here you can see this is the liquid solution. Definitely the solvent should be the liquid. Gas and liquid, that is oxygen dissolved in water, that in general you can see in any kind of water body. Right, next you can see liquid, that is ethanol dissolved in water. Next you can see solid liquid, that is glucose dissolved in water. Okay, next let's proceed. Solid solution, if you proceed, gas and solid, that is a solid solution of hydrogen and palladium. We know the palladium surface can adsorb hydrogen gas, right? So that can be taken as solid solution. Okay, next you can see liquid solid, that is the amalgam of mercury with sodium, because you know amalgam, I mean whenever it comes to the matter of mercury, it is liquid in general state. Next you can see solid, that is copper dissolved in gold. Okay, I guess this particular portion is clear. Okay, I can see Asha Rajput, my pending syllabus is PGMB, all chapter 3 model question paper, subject 3 PYQ per subject revision 2 preparative exam. What I do for 90%. Okay, but as of now, what I can suggest you, please proceed with the first chapter, that is one of the most important chapter for your both PU2 and KCET. So one by one we will do the chapters and your concept will keep like covering up. So please don't be too much worried about it. It will be good. Okay, so yeah, let's proceed further. So here you can see the most important thing starts from here actually, that is a concentration terms. Okay, that is percentage by mass, mass percentage, volume by percent, mass by volume percent, and parts per million, and mole fraction and molarity. Okay, and molality also we will get. Okay, so these things you have to proceed. So let's proceed. Here you can see the first thing, that is the mass percentage. Okay, so mass percentage, when it comes, always remember in the both case, when in the numerator and denominator, you will be having the unit of mass only, means either gram or kg, the unit should be of the mass. Okay, so here you can see mass of the component in the solution and divided by total mass of the solution into 100. So these particular thing, I want you, whoever is watching my lecture, please keep making the notes. Okay, please keep making the notes so that it will be helpful for you whenever the exam will be coming. Okay, so let's proceed. What does it mean actually? Like if you can see, if a solution is described as 10% glucose in water by mass, okay, then here you can see actually it is written something like percentage W by W, like 10% in bracket W by W. Okay, so here you can say that 10 gram glucose is dissolved in 90 gram of water, resulting 100 gram of solution. Be careful about it. Here in the denominator part, you are putting the mass of the solution. Okay, mass of the solution, not the mass of the solvent. In order to find out the mass of the solvent, you have to subtract the mass of the solute from the solution itself. Okay, yes, I can see Nusrat. Yes, definitely. Definitely you can get more than 95%. Definitely. I will try my best, my dear. Okay, I will try my best to get you the marks 95% in board and KCET. I will try my best, my dear. Okay, definitely you will get. And I can see Kalki. I think Mang become teacher in this year. No, but I am not the teacher in this year. Like it is the first year in YouTube. But I have 6 years of experience. Don't worry. Okay, let's proceed further. Here you can see the next thing, that is mass by volume percentage. Okay, so percentage of the component, here you can see that is basically mass of the component in the solution divided by volume. So here please be assured that in the numerator part you will be having the unit of the weight, and the denominator part you will be having the volume unit. Okay, Okay, so here you can see if you are having this type of thing like a liter of a C, sorry, just a minute. Okay, so this is my mass by volume. So I really insist you to please make a note of it. Please make a note of it, that the particular formula, because we are going to apply this formula in the numerical problems. Let's proceed further. Here you can see this is parts per million, that is ppm. Okay, so this ppm unit is used like sometimes to measure the dissolved oxygen amount in water, or amount of the pollution, or amount of dust particle present in the atmosphere, this type of thing. Okay, very small units. Okay, so here you can see parts per million, number of parts of component divided by total number of parts of all component of the solution into 10 power 6. Also you can get parts per billion as well, so that 10 power 6 will be 10 power 9 that time. Okay, so let's proceed further. So here you can see a liter of sea water which weighs like 1030 gram contains about 6 into 10 power minus 3 gram of dissolved oxygen. Such a small concentration is also expressed as 5.8 gram per 10 power 6 gram of sea water. Okay, that is 5.8 ppm, parts per million. Okay, so this is how you can proceed. So I guess you have noted this formula. So let's apply, let's implement this formula. So here you can see, calculate the mole fraction of ethylene glycol in a solution containing 20% of C2H6O2 by mass. Ethylene glycol, 20% ethylene glycol by mass. So I insist you people, if you have understood a little bit, please give it a try by yourself, and then definitely we will proceed accordingly. So first, that thing I can do is, I can actually calculate the number of moles at first. So many of numerical type of problem we are going to solve from this chapter. Whatever the probable zone from this particular case, we are going to solve everything. Okay. Okay, which term is commonly used in the medical field? In the medical field, generally we use weight by volume percentage. Okay, so that is the most used term in the medical field. Different type of ointment and all, if you see that, the concentration term is used weight by volume. Okay, so now let's proceed. Here you can see, so first we can calculate the number of moles of ethylene glycol at first, and number of moles of water as well. Okay, so from here 20% they are saying, right? So 20% of ethylene glycol, 20% of ethylene glycol, weight by weight, right? Weight by weight, it indicates I am having 20 gram of ethylene glycol. I'm just writing ETG, okay? 20 gram of ethylene glycol plus 80 gram of water. By default, it is said. Okay? So now what I can find out? I can find out the number of moles of glycol. Okay, so if you want to find out the number of moles of ethylene glycol, you will need the molecular weight. Molecular weight of ethylene glycol is 62 gram. So given weight is 20 gram and molecular weight is 62 gram per mole, right? This is 62 gram per mole. Okay, so if you calculate this, your thing will come as 0.3226. 0.3226 gram. Okay, this is the number of moles of ethylene glycol. Next you can see number of moles of water. So that is by default it is given as 80 gram divided by, you know, molecular weight of water is 18 gram, right? 18 gram per mole. Okay, so if you calculate this, it will come almost like 4.44. It will come almost like 4.44. Sorry, this should not be gram, this should be mole. fraction, right? So mole fraction formula is mole fraction of ethylene glycol, that is number of moles of ethylene glycol divided by number of moles of glycol plus number of moles of water, right? So now just put the value. So if you put the value 0.3226 divided by 0.3226 plus 4.44, okay? So now if you calculate this, your answer will come as 0.067. 0.067. Okay, okay, I can see Nusrat, very good. Okay, so please keep solving with me. This is going to be the answer for this particular numerical. Ma'am, PYQ or solved? PYQ, yes, definitely. PYQ we will include in this particular series as well. Means throughout the journey you will see so many PYQs for the board and KCET I have included here. Okay. So next question here you can see molarity. Okay. So this is the formula of molarity, that is the number of moles of solute present in 1 liter of the solution. So in the denominator part you must have the solution, the volume. Okay, so in case of number of moles you can break it down like given weight by molecular weight, right, into 1000 divided by the volume of solution. Please note down the formula. Next let's proceed. Okay, so here molarity, like for example if it is given as 0.25 mole per liter or 0.25 molar solution, if it is given, then you can tell that 0.25 mole of that particular solute has been dissolved in 1 liter of the particular solution. Okay, let's proceed further. Here you can see one more question. Calculate the molarity of a solution containing 5 gram of NaOH in 450 ml. Okay, so you can directly apply the formula of the molarity. So molarity can be written as, you know, W2 by M2 into volume of solution. If it is in the ml, then you have to multiply with 1000, right? So this is how you can proceed. So you can see W2 means 5 gram. Molecular weight of NaOH is 40 gram per mole. Volume of the solution is also given 450 ml. And here it is 1000. Okay. So now if you just calculate this particular case, your answer will come almost as your answer will come as 0.278. Okay, 0.278 mole per liter, or molar you can write. Okay, anyone. I guess it's okay. Let's proceed further. Okay, I can see someone is answering 0.278. Very good, my dear. Let's proceed further. Okay, here you can see this is molality. Okay, so molality is moles of solute divided by mass of solvent in gram. Okay, into 1000. Okay, so moles of solute, again we can break it down, divided by given weight by molecular weight into 1000 divided by mass of the solvent. This is how we can proceed. Okay, so next, if anyone says that I am having 1 molar solution, what does it mean? It means by default it is given information that I am having 1 mole of the solute. Means let's say they are saying KCl, I guess. Yes, KCl means 1 mole of KCl I am having, means molecular weight of KCl is present in 1 kg of water. Okay, let's proceed. Here you can see this is basically one numerical problem once again. So calculate the molality of 2.5 gram of ethanoic acid in 75 gram of benzene. So now you can do it nicely, directly just apply the formula over here. So molality I can write it in this form. So I need the molecular weight of ethanoic acid. So molecular weight of ethanoic acid is 60.06. Okay, so now if you just put everything over here, 2.5 gram divided by 60.06 gram per mole, okay, into 75, because they are saying the solvent mass is 75 gram into 1000, as simple as that. Okay, so if you just calculate, it will come almost like 0.55 gram, 0.55 mole per kg, sorry, 0.55 mole per kg or molar. Okay, I can see that you are giving correct answer, very good. Okay, let's proceed further. So here you can see these are some previous year question from the board. Okay, so whenever it will come, I will mention that yes, this particular question is from the board, this particular question is from the KCET and all, I will tell you. Okay, so let's proceed. Here you can see concentration term like mass percentage, ppm, mole fraction and molality do not depend upon temperature. However, molarity is a function of temperature. Why? Okay, whenever you are just looking forward to molarity, you can see that in the denominator part volume is present. Means molarity is inversely proportional to volume. Okay, and volume is directly proportional to temperature. Right, volume is directly proportional to the temperature. So definitely if we correlate, molarity is inversely proportional to temperature. Okay, so definitely as volume is there, then definitely you can tell that yes, it is temperature dependence. So A is going to be the correct one. Okay, very good. So many of you are giving the correct answer. Pradyun, okay, very good. Let's proceed. Here you can see this is also a pre-board question, I mean PU2 examination, that is from the previous year. So here you can see calculate the mole fraction of benzene and carbon tetrachloride in a solution made by dissolving 20 gram of benzene in 80 gram of carbon tetrachloride. Okay, so let's proceed. So for this particular case, we have to calculate the mole fraction, and for the mole fraction we need the number of moles, right? So here you can see everything is given out there, right? So number of moles of benzene, if you just first calculate, that is 20 gram is given, and the molecular weight is given is 78 gram per mole. Okay, so something will come, I am not calculating here. And the number of moles of carbon tetrachloride, CCl4, it is coming as 80 gram of it divided by 154 gram per mole. Okay, so now if you just put the formula over here, like mole fraction of benzene C6H6, so that must be number of moles of benzene divided by number of moles of benzene plus number of moles of CCl4. Okay, if you just put those terms here, okay, you will get the answer. You can see mole fraction of benzene, you can see you will get 0.33. Okay, for mole fraction of CCl4 also you can proceed with the same way. Number of moles of CCl4 divided by number of moles of CCl4 plus number of moles of benzene. Okay, if you just put the value over there, then also you can get the 0.67. Okay, once another thing you can do is like you can avoid calculating this particular thing, rather than you can do one thing, that you can do 1 minus 0.33. that will also give you the answer, because you know XA and XB, if you are having binary compound, right, binary solution, then you can have the mole fraction summation always equals to 1. So 1 minus 0.33 will also work. Okay, let's proceed further. Let's proceed. Here you can see this is from the KCET. Okay, KCET previous year question from the concentration term. Okay, so here you can see an aqueous solution of alcohol contains 11 gram of water and 414 gram of ethyl alcohol. Okay, the mole fraction of water. So for this type of question, what do you have to do? The aqueous solution of alcohol. Okay, 11 gram of water, so number of moles of water at first you have to calculate, and number of moles of alcohol, ethyl alcohol, I am just writing ETOH, you have to calculate. Okay, so here you can see 11 gram, okay, 11 gram of water divided by 18 gram per mole. Okay, so if you calculate in this case, 11 divided by 18, right, it will come as 0.611. Okay, now for the ETOH, the molecular weight is 46, right, and you are having 414 gram divided by 46 gram per mole, right. So now if you just calculate this thing as well, just let me calculate, just a minute, 414 divided by 46, right. Okay, you will get 9 over here. Okay, here's 0.611 mole and here you are having 9 mole. Okay, so the mole fraction of water, so mole fraction of water will be something like 0.611 divided by 0.611 plus 9. So you can get the answer like 0.611 divided by 0.611 plus 9. Okay, so you are getting the answer 0.06. So option C is going to be the correct one. Okay, I can see Pradyun is giving the correct answer. Very good, my dear. Okay, let's proceed further. Okay, so here you can see, here comes our next topic, that is the solubility. Means concentration term is over. Whatever the previous year question it came, that we already discussed. Okay, next here you can see in the solubility, we can discuss the solubility of solid in liquid and solubility of gas in liquid. Okay, so first we will proceed a little bit, solubility of solid in liquid. Okay, so solubility of solid in liquid, first it depends upon the nature of the substance, next is temperature, and third one is pressure. Okay, when we are discussing the solubility of nature of the substance, means whatever my solute is. Okay, so it is basically something like dissolves like concept. Like dissolves like concept in the sense means if you are having a polar solvent, okay, you need polar solute. Okay, let me just give you an example. If you are having, let's say, oil and water, okay, they are not miscible. Why? Because oil is non-polar and water is polar, right? So they are not miscible, right? Hydrophobicity is there, right? But whenever it comes to the, let's say, NaCl, right? So NaCl is a charged molecule. It means whenever it will be getting ionized, it will be Na plus Cl minus, and water molecule can stabilize them because it's polar. Okay, so that's it. So whenever again you are having like organic solvent like benzene, okay, they can again soluble the oil because both of them are of same nature, they are non-polar. Okay, so this is a like dissolves like concept. Okay, next you can proceed, that is the temperature. If temperature factor comes, then here comes a very important thing. If del H is greater than 0 means endothermic, del H is greater than 0 means del H value positive means endothermic, then solubility increases with temperature, then solubility of solid increases with temperature. If del H is negative means exothermic reaction, then Okay, I understand you need time to note, fine. Okay, if del H is negative, that is exothermic, then the solubility decreases with temperature. Okay, so what I told, just write the gist from here. So I tried to make it as much simple as possible in the form of a brain map. So here you can see, whenever del H is greater than 0 means endothermic, then it increases, solubility increases with temperature. When del H is less than 0 means it is negative, then it decreases with temperature. Okay. Okay, so Asha Rajput, how to score 90% in last 50 days? Please help, ma'am. We are here to help you out, my dear. So please follow our 02 Hero series that will help you to get 90% in your PU2 as well and your KCET as well. So as you can see, we are like dealing with the detailed chapter. You can feel it's a classroom experience. You can see like every thorough concepts we are going thoroughly, and here if you just put some doubts also, then we can also like target them. Okay, let's proceed. Next, pressure. So whenever it comes to pressure in solid and liquid solution, there will be no effect in because of the pressure. Whenever it comes to gas, then it will come and we will proceed further with the Henry's law and all. Okay. So this is all. Let's proceed. Kaushik, what happened to your hand? Just a little bit injury, my dear. Let's proceed. Here you can see effect of pressure. Now whenever it comes to the matter of effect of pressure, then definitely it matters a lot. Just let me just give you an example. Let's say I'm having this particular container and this is the liquid over here. Okay, this is a closed container, piston over there, and here I'm having some other gas particle, right, other gas particles. So now if this was the initial condition, right, this was the initial condition. Now if you are just increasing pressure, then what will happen? This particular gas will come to start being dissolved in the liquid. So this will come here, right, because they are not getting enough space, right. So once you are increasing the pressure, it's a general thing. If you're just increasing the pressure, where these gas particles will go? They will get dissolved in this particular liquid, right. So let's proceed. Here you can see from this concept itself, the Henry's law is generated. You can see Henry's law is a gas law which states that at the amount of gas that is dissolved in liquid is directly proportional to the partial pressure of that gas above the liquid when the temperature is kept constant. Very important Henry's law statement. Sometimes they ask this question as well directly in 2 marker. Okay, so what basically happens, I guess you understood. If you just like increase the partial pressure, then keeping the temperature constant, the solubility of the gas will increase. Okay, now here you can see the formula of this Henry's law, that is partial pressure of the gas. See, partial pressure of the gas is directly proportional to, here solubility is indicated as the mole fraction. Solubility means what will be soluble? The number of moles of gas will be soluble in form of what? Number of moles, right? And number of moles can also be explained in the term of mole fraction, right? So that's the reason solubility expressed in the term of mole fraction in this Henry's law. Okay, if you remove this proportionality sign, then here will come one constant, that is kH into mole fraction of gas. This kH is called the Henry's constant. Okay, so whenever you are just writing the numerical form of any law, please make sure you are writing down the abbreviation of it. Means what is P, what is KH, what is X. Okay, it's very important. Okay, so I guess it's clear to you. Let's proceed further. The same thing here it is given actually. if you just increase the pressure over here, if you just increase like weight, amount of weight if you increase, then amount of gas that will come to the solution will be increasing. Okay, let's proceed further. Here you can see applications of the Henry's law, very very important. Let me write it, let me mark it as board alert. Okay, very very important question. I have seen this question coming so many times. Okay, so here you can see, first to make the carbonated beverages, right? So like if you increase the pressure, then in high pressure CO2 can get dissolved in different type of soft drinks like soda water, okay, and all. So this is one of the application of the Henry's law. Another one here you can see, scuba diver. Okay, so here what basically happens means like the tank used by scuba divers are filled with the air diluted with helium. So basically in general the tank that is used by a scuba diver, it is having definitely oxygen and nitrogen majorly. Okay, so what happens when a scuba diver go deep down to the water, then the pressure of the water increases, right? As a result of this, what happens, as pressure increases, nitrogen gas starts to get dissolved in your blood. Okay, the nitrogen gas starts to get dissolved in the blood. But when that particular diver comes up from the deep of the water, when it is coming up, then pressure is slowly decreased, right? The water pressure will be decreased, and that particular case what happens, nitrogen gas that was dissolved initially, it starts to gets bubbled out from the blood. Just imagine how much painful that thing can be. Okay, that particular gas starts to get bubbled out from the blood itself, and that particular thing is very painful, and the medical condition is called as bent. Okay, so to prevent this, what they do, they just mix some helium, they dilute it with helium. As a result of this, it prevents the solubility of the nitrogen in high pressure. Okay, so it is one of the application of the Henry's law as well. Next, here you can see another one application, that is the anoxia. Okay, in the higher altitude, what happens basically, pressure becomes very low, right? The air pressure becomes very low. What happens then? Then the oxygen that should get dissolved in our blood in general condition, that amount also gets reduced, right? So your brain doesn't get enough oxygen supply. As a result of this, you can have like some problem like dizziness, you can feel some nausea, you will lose the ability of thinking. This is called anoxia. Yes, 3 conditions are there. Anyone, like on the basis of the mark, if it comes as a 2-marker question, you can mention any 2 application out there, and if it is coming as 3-marker question, usually it comes as 2, but if it comes as a 3-marker question, mention all the 3. Okay, let's proceed further. Here you can see effect of temperature. Next we will proceed, effect of temperature. What happens basically, the Henry's constant value increases with the increase in temperature. Okay, as a result of this, solubility decreases. What happens basically, if you just see, partial pressure of the gas is basically equals to kH into mole fraction of the gas, right? So from here you can see kH is inversely proportional to the mole fraction of gas. From here I can tell, if temperature increases, kH increases, and kH and mole fraction, they are inversely proportional, hence solubility decreases. Okay, this is one of the very important thing, please remember that. So finally, how I can connect it? If you increase temperature, solubility decreases, and if you decrease temperature, solubility increases. One of the MCQ question was there in the model paper, very important, probably in your pre-board examination it was also there. Let me just discuss a little bit about it. Means, let's say if you are having 2 container A and B, both of them are having water. Okay, so container A you have freezed, okay, and B you have heated. Okay, then the MCQ was something like, in which container you will be having maximum like oxygen dissolved in it. Okay, it was a question from the model paper itself. In your pre-board examination also it came. It is related to this concept. Okay, so here you can see in A, as temperature is freezed, means temperature is decreased. In B, temperature is raised, right? So in this particular case, here temperature is decreased, means solubility increases, means here I will be having more oxygen. Okay, I guess it's clear to you. Let's proceed further. Here you can see one question comes. If N2 gas is bubbled through water at 293 Kelvin, how many millimoles of N2 gas would dissolve in 1 liter water? Assume that N2 exerts a partial pressure of 0.987 bar, given that Henry's law constant for N2 at 293 Kelvin is 76.48. Okay. Okay. Make your own notes. And also please keep answering for the questions as well. Yeah, I understood, my dear. Okay, you just make the note. By the time, please let me know if you're understanding the things or not, if the concepts are getting clarified to you or not. Your response is very much important because I want the session to be very much interactive. We will see. I will come back to it, don't worry. In the next question we will calculate the millimole. Nothing, just multiply with 10 power 4, that's it. Okay, very good. So let's proceed. I guess it's enough time. In case you are unable to see all the time, it's not possible like to check out the comments. Maybe whenever I will be there in the flow, I will be proceeding. Please like take the screenshot, okay? But I really appreciate your effort that you people are making the note. That's gonna be helpful for you. Okay, so let's proceed. Here you can see the question. So someone is asking the millimoles, right? Okay, we will solve it here. You can see if N2 gas is bubbled through the water at 293 Kelvin, how many millimoles of N2 gas would be dissolved in 1 liter of water? So here we are going to apply definitely your Henry's law. First, what is the formula? You know, P of N2 is basically mole fraction of N2 into KH. Okay, from here I can actually calculate the mole fraction of N2 by P of N2 by KH. Okay, so let's put the value here. Pressure of N2 is given as 0.987 bar. 0.987 bar divided by KH value is given. Henry's law constant is 76.48. Okay, wait, it's kilobar. Let me just convert it. Just directly write it. Okay, be careful about the unit. These are very small things that you have to take care, because here you can see it was kilobar. Okay, so if you calculate this, your answer will come almost similar to 1.29 into 10 power minus 5. Okay, now from here I can get the moles of water as well. Okay, so from here what I can do, that is the mass, that is definitely 1000, because they are saying 1 liter. 1 liter of water means 1000 gram. So from here I can get 1000 gram divided by the molecular weight 18 gram. Okay, from here it comes actually 55.5 mole. Right, now you can just calculate the mole fraction. Okay, so mole fraction of what I have to find out, N2, right? Mole fraction of N2, it's basically equals to number of moles of N2 divided by number of moles of N2 plus number of moles of H2. So here one thing I wanted to tell you, whenever a gas is about to be dissolved in water, whenever a gas is about to get dissolved in water, then you can see the number of moles of water is so much than that of the number of moles of N2, right? So we can almost neglect this term, right, in the denominator. So that can be written as number of moles of N2 divided by number of moles of water only, because number of moles of water is too much high than that of the number of moles of N2. Right, so let's put the value, that is 1.29 into 10 power minus 5 divided by 55.5. Okay, so from here if you calculate, it will come as mole fraction of number of moles you have to calculate. Wait just a minute. From here you can proceed with number of moles of N2 is basically equals to mole fraction of N2 into number of moles of H2O. So number of mole fraction of N2, you can see it's 1.29 into 10 power minus 5 into 55.55. Okay, so from here you will get 7.16 into 10 power minus 4. 7.16 into 10 power minus 4 mole. Okay, so for this particular case, if you want to convert this to millimole unit, then you have to just multiply with 10 power 4. That's it. Okay, so as a result of this, you will get, okay, milli means 0.716, 10 power 6 you have to multiply, 10 power, 0.76 is going to be your answer. Okay, I guess it's clear. Yes, very good Pradyun. Okay, so I guess you got it. Okay, someone, you need the WhatsApp channel. Yes, I will tell to put the channel link as well. You will get it. Okay, let's proceed further. Let's proceed further. I guess it's clear to you. Okay, so here comes, this is also a board question. molar solubility of helium, nitrogen and oxygens are plotted against the partial pressure of the gas at constant temperature. Henry's law constant for these gases. Okay, so here you can see here you can see we know P of gas is basically kH into mole fraction of gas. So with respect to that, plus 0 I can do, right? So this is a straight line equation right now, right? So this is, you can see it is my Y, that is the solubility mole fraction, right? Wait, this is the X here. Okay, okay, we can change it over there. In general, it is a partial pressure. This should be the, this thing should be the, this particular thing should be the M and this particular thing should be the X, right? So in general, this should be the overall thing. So if I just plot this thing, this Y axis, here should be the partial pressure PP, here should be X, and you will get a straight line passing through the thing, passing through the origin. Okay, and here you can see, here in this particular case, the slope will be KH. Okay, but here you can see that solubility and partial pressure, they are actually interchanged. So here for this case, my slope will be, slope will be 1 by KH, right? Because these things are changed, interchanged, the axes are interchanged, right? So now from this particular case, I can find it. Here you can see O2 is having maximum KH value, right? O2 is having, 1 by KH, right? And N2 is having again like less than HE, right? So O2 is having lowest, then you can see you will be having N2, then you will be having HE. Okay, if they could give the partial pressure here and solubility below, then your answer would be the exact opposite one. Okay, I guess you understood this. So your answer is going to be B. Okay, is it clear? Please, please, please let me know. My dear, if you want to ask any doubt, please ask me here itself. Okay, I can see someone of you. Akshay Raj. Okay, option B. Very good. Say your number. Okay, beta, I don't use mobile phone. What to do now? Okay. Can you explain that once again? Definitely I can explain that once again. So in general, what happens? In general, if you see the straight line equation, P equals to KH into X, that is the actual Henry's law. From there you can see it is following a straight line equation. P is the Y, KH is the slope, okay, X is the mole fraction is X axis, okay, and intercept is 0. Okay, so now here you can see this is the graph how it should look like. It should pass through the origin. Okay, it should pass through the origin. Okay, so in this particular case, if you follow this particular equation, no, then your P means partial pressure should come in the Y axis and your mole fraction should come in the X axis, right? But whatever it is given in the question, it's not like that. Here you can see solubility is given in the Y axis and partial pressure is given in the X axis. So slope should be 1 by that particular value. Initially slope was only KH, but now whenever the axes are interchanged, then the slope will be 1 by something, 1 by KH. Okay, so KH is maximum for O2, but whenever you are doing 1 by KH, it will be minimum, right? It will be minimum for O2, right? Then look at the N2, look at the slope. KH should be maximum for O2, but 1 by KH is minimum for O2, right? N2, then HE, right? I guess you understood this. Is it clear? Ruhi Tab 15. Can you please tell me if it's clear to you? let's proceed. Just let me know if it is clear to you in the comment section. Here you can see from the solubility, this is a question for the board as well. This was also for the board examination only, very small answer type question. Okay. Okay, I can see how much weightage. Okay, so how much weightage beta at the very beginning I already told, one of the heavy weightage chapter is the solution. 12 question almost, 12 mark it will come from the solution chapter, and in the last few years, last 5-year analysis, the KCET also having the very very high number of questions coming from the solution itself. Just let me show you just for a reference. You can see at the beginning I told this thing. This was the weightage, overall weightage. Just you can take a screenshot out there. Okay. So let's go back where we were. We were here. Okay. Here you can see states Henry's law, write its mathematical form, and what is the significance of the Henry's constant. So this is something, it comes, which one I have to explain again? This one, right? Okay, definitely I can explain for you, my dear. So this is basically Henry's law. If you follow the general equation, in this particular case P is y-axis, okay, mole fraction should be in the x-axis. There in this particular graph slope should be kh. But here whatever is given in the question, it's actually the axis is altered. You can see solubility should be there in the x-axis, but here it is given in the y-axis, and partial pressure is given here. So kh should be reciprocal, right? Slope should be reciprocal of it, right? So now if O2, if you just look at the O2, okay, normal case, if I plot the O2 here, the kh is maximum, right? But here I am plotting it in a reverse graph. So O2 should be minimum. kh, 1 by kh is minimum here. 1 by kh is minimum for, then after that N2, then helium. Right? So that's gonna be the correct order. Okay, I guess it's clear to you. Let's proceed. This is a general thing I already told you. Here you can see the answer. Here significance of the Henry's constant, it can give the solubility of a gas at a given pressure. Okay, like a higher kh value means lower solubility because they are inversely proportional, that I already told you. Okay, I guess it's clear to you. Yes. Yes, KCET cutoff for 2026. Let the exam gets over, my dear. Let's proceed further. You can see, here you can see the next question. It is a numerical based question, that is also a board level question. The mole fraction of helium in a saturated solution at 20 degrees Celsius in 1.2 into 10 power minus 6. Find the pressure of the helium in the above case. So here simple, you just have to apply pressure of helium is basically kh into mole fraction of helium, right? Now just put the value. So the kh value you can see it's given over here 144.97 bar, okay, into mole fraction is given as 1.2 into 10 power minus 6. So if you calculate this, your answer will come 0.00017396. Okay. Okay, this is kilobar. You will get kilobar. That's the answer. Very simple. Okay, let's proceed further. Let's proceed. Here you can see the next question, that is also the previous year question from the KCET. Okay, so variation of solubility with temperature T for a gas in liquid is shown by the following graph. So what I told, solubility and temperature, they are inversely proportional. So if temperature is increasing, solubility will decrease. Okay, now check where it is happening. Okay, so this particular case you can see, if you are increasing the temperature, solubility is decreasing. Okay, so that's gonna be the correct answer. Okay, I guess it's clear to you. Let's proceed further. Here you can see the next question. So as you can see, solubility, temperature, solubility of gas, this particular zone is one of the very important zone for the KCET examination as well. Like 2 questions I can show you, like this is one of the previous year question as well as this one. Okay, so here you can see solubility of gas in a liquid increases with, okay, so if you just see this graph, P of gas equals to kH into mole fraction of gas, right? So you can see they are directly proportional. Okay, so definitely solubility increases with increase in the pressure, and they are inversely proportional to that of the temperature. Okay, means if P increases, solubility increases. If temperature increases, solubility decreases. So this is the correct answer, right? Let's proceed further. Yes, very good. I can see so many of you are giving correct answer. Very good. Okay, I can see I am student of Deeksha Vidyanagar. Very good to see you, my dear. Like a very small period of time I was there in your campus. So if you know me, then it feels really good. Yes, Asha Rajput, definitely I will be solving. All the questions are there actually, means I have kept all type of question, previous year as well, your preparatory question. Preparatory, there will be a different live session for you, my dear. Okay, there I will be solving so many of questions, so many of like, you know, important question, most important, most relevant question I will give you out there, don't worry. Okay, you know me, it sounds really good that you know me. Okay, thank you so much. Let's proceed further. Here you can see the next one. That's also a question from the KCET itself. So Henry's law constant for the solubility of N2 gas in water at 298 Kelvin is 1 into 10 power 5 atmosphere. The mole fraction of N2 in air is 0.8. The number of moles of N2 from air dissolved in 10 moles of water at 298 Kelvin and 5 atmosphere pressure. Will you give it a try? Will you give it a try? First calculate one thing, calculate the pressure of N2 at first. Okay, calculate the pressure of N2. How you can calculate pressure of N2 is basically kH into mole fraction of N2. Right? Put the value over there, that is already given. Okay, from the partial pressure we can do it. We can calculate actually the partial pressure of N2 at first, then we can put it into the Henry's equation, right? So for this particular case, I can get pressure of N2 is basically mole fraction of N2 into P. So for this particular case, I can get mole fraction of N2 is given as 0.8 into 5 atmosphere pressure. Okay, so from here I can get the value 4 atmosphere. Okay, now you can apply the Henry's law. Mole fraction of N2, that is pressure of N2 divided by kH, right? So pressure of N2 you can put it from here, 4 atmosphere, and kH value also you can put 1 into 10 power 5, 1 into 10 power 5 atmosphere. Okay, so definitely your answer is going to be 4 into 10 power minus 5. Okay, I guess it's clear to you. It's going to be B. I insist you people just check the answer. In accordance to me, it's coming 4 into 10 power minus 5. Check it once, okay? Let's proceed further. Just let me know if you have done with it. Okay, my dear, partial pressure of nitrogen, if you want to find out the part in Henry's law, what we use na, in Henry's law, this is the Henry's law, right? Here the pressure that we use, it is the partial pressure of N2. Okay, one formula let me just tell you, partial pressure is equals to, partial pressure is basically equals to mole fraction of that gas into total pressure. Okay, from this is a formula to get the partial pressure, then you can implement that partial pressure into the Henry's equation. Okay, so not getting it. So basically partial pressure you have to find out at first. Partial pressure value is not it's given here directly. Okay, partial pressure at first you have to calculate. Okay, because they are saying here, you can see 5 atmosphere pressure, it is the total pressure, it's not the pressure for the nitrogen, it's total pressure, right? So from the utilizing this, you have to find the partial pressure. So partial pressure of nitrogen, this is a formula, mole fraction into total pressure, Okay, if you calculate this, then you get the partial pressure of N2, and then further you implement that in your Henry's law. Okay, so yes, absolutely, it's a part of Raoult's law, but not like as it is combined with the Henry's law as well, that's why I kept here. Okay, yes, very good. So Shakshi, can you please tell me if you understood this? Just let me know if you understood this. So now from here, if you just further calculate pressure of N2, like it is the Henry's law that you know, right? So from the Henry's law, if you further calculate, then you will get 4 into 10 power minus 5. Okay, so I guess it's clear. Let's proceed further. Here you can see we are coming to the part 2, that is related to the vapor pressure, ideal, non-ideal solution and all. You can see vapor pressure whenever it comes, then vapor pressure in liquid solution, okay, vapor pressure in solid liquid solution. Okay, so these two things can come out there. Okay, so here you can see whenever we are discussing the liquid and gas vapor pressure, so they are always in an equilibrium state. So basically, if I just take a bottle of water, okay, so let's say that above a little bit portion it's empty. Okay, above a little bit portion it's empty, so that empty portion is covered by the water vapor itself. Okay, and they are in constant equilibrium with the liquid and the vapor phase. Okay, so now here you can see at the equilibrium the evaporation rate is equals to the condensation rate. Definitely the same way the liquid gets evaporated, in the similar way the gas will come down in the condensate, it will get condensed and it will come to the liquid form. Next you can see molecules in vapor phase collide with the walls and lid of the container, causing the pressure. Okay, so the pressure out there that is generated just because of the collision of the gas particles to the wall of the container, right, that is called vapor pressure. Okay, next you can see evaporation and condensation occur at the liquid surface. Definitely the entire bulk of the liquid doesn't take part, usually the surface of the liquid, from there itself the entire equilibrium process actually takes place. Here you can see increasing the temperature increases the rate of evaporation and increases the vapor pressure as well. So if you give the temperature, like what will happen, the more amount of liquid will go to the vapor phase and more vapor will be generated, it will create some more pressure on the container wall and hence the vapor pressure will be increasing out there. Okay, I guess it's clear to you. Okay, Ruhi, ma'am, till what time will the session go? So again I'm telling you, my dear, I can end it right now, but I want you to master this subject, master this particular chapter. So definitely I will clarify your concept properly. We will solve all probable MCQ numerical type, short answer type question and KCET PYQs as well, then I will stop, my dear. Okay. Next, let's proceed. Let's proceed further. Here you can see this is the Raoult's law. Okay. So whenever it comes to the matter of liquid solution, then the Raoult's law comes to the place. Okay. So what happens for a solution of volatile liquids, vapor pressure of each component of the solution is directly proportional to the mole fraction. Okay. So Raoult's law direct statement usually it doesn't come. Okay, Raoult's law, the direct statement, it is usually doesn't come. So basically, the numerical type of problem you can expect out there from the Raoult's law. Okay, so I guess it's clear. Now, if you remove this proportionality sign, then there will come one constant. So what constant? The constant is basically that particular liquid vapor pressure when it is in the pure state, vapor pressure of that particular liquid when it is in the pure state. Now it is mixed, right, in the solution state, but individually whenever the liquid is there, it is having some vapor pressure. Okay, so in that case, that particular pressure is constant and that is taken here, okay, into x1, right. I guess it's clear to you. So now here you can see this is how we can we can explain the Raoult's law in the numerical form. Okay, pressure of A is directly proportional to the mole fraction of A and the constant will come as P0. Okay, next here you can see for the B, because we are taking a binary solution, means mixture of A and B. Okay, so it's directly proportional to XA and directly proportional to XB and the constant will come as well. Okay, next here you can see, here comes the Dalton's law. Wait, someone was asking me about that question only, like that partial pressure. You can see according to Dalton's law, the partial pressure, the total pressure over the solution phase in the container will be the sum of the partial pressure of it. Okay, so basically means I am having A and B in my container. I am having A and B, two volatile liquid in my container. So the total pressure that is generated out there, total pressure generated both from A and B, total pressure generated from both A and B, that will be basically equals to P of A plus P of B, right? That is the Dalton's law. So now P of A is what? That is P0 of A into mole fraction of A plus P0 of B into mole fraction of B. Okay, that's gonna be your Raoult's law. Okay, I guess it's clear to you. Now it's clear, I guess. Let's proceed further. Here you can see modified formula. So modified formula, just nothing. You can see from here in case of XB, mole fraction of B, right, we can write it as 1 minus XA. So why I am doing it? In order to get a equation, straight line equation, so that I can plot the graph basically. Okay, so here you can see further, if you just simplify it, you will get this type of equation and it's a straight line equation with the intercept P0. Right. So now if you just plot the graph, it will be this. So now here you can see, in case of XB, you can write 1 minus XA and you are getting this equation. Okay. Now if you do the same thing but keeping this XB and replace this XA with 1 minus XB, you will get another one equation, right? Two straight line. Now combine these two straight line and you will get this thing. Okay, with the P10 as and P10 and P20 as the intercept of it. Okay, connect them, you will get the total pressure. Okay, so this is how the Raoult's law graph it comes. So please be careful, it's a high alert zone for the board. So basically the question is asked something like, whenever two different volatile liquid, they are mixed, then what type of graph you can expect out there. Okay, I guess it's clear. Let's proceed a little. So here you can see another one important thing, that is the vapor phase composition. Okay, vapor phase composition. So vapor phase composition of YA and B means, let's say here you can see I am having, in my particular case I am having both the liquid A and B. Okay, here in this case I am having both A and B, and in the vapor also I am having the vapor of A and vapor of B as well. Okay, I am having both the vapor of A and vapor of B. Now if I want to ask you what is the composition in the vapor of A and B, how will you find it? So you have to find it in this way, that is pressure of A divided by total pressure, and here also pressure of B divided by total pressure. Total pressure means divided by PA0 of XA plus PB0 of XB. For this case also, here you can write PB divided by PA0 of XA plus PB0 of XB. Okay, always remember YA plus YB, whatever the components, maybe you are having more than 2 volatile liquids as well, it's not a binary solution anymore, then that case also you can add them and you will get the summation as 1, always like the mole fraction. Okay, I guess it's clear. Let's proceed further. Here you can see again one numerical type problem. I want you people to give it a try. Okay. So here you can see the question, vapor pressure of chloroform and dichloromethane, vapor pressure of chloroform and dichloromethane at 298 Kelvin at 200 mm of Hg and 415 mm of Hg respectively. Okay, calculate the vapor pressure of the solution prepared by mixing 25.5 gram of CHCl3 and 40 gram of CH2Cl2 at 298 Kelvin. So definitely here you can just simply apply the Raoult's law, but we need the number of moles at first. Okay, so a lot of things actually we have to do here. We need the number of moles. Okay, then from the number of moles we have to calculate the mole fraction, and then with respect to the mole fraction we have to put it into the Raoult's law. It's gonna be a lengthy one. Okay, fine, let's proceed one by one. So number of moles of CHCl3. So basically here what is the value given? 25.5 gram. So sorry 25.5 gram divided by molecular weight of chloroform. So molecular weight of chloroform is 119.5 gram per mole. Okay, so if you come up with it, it will give you something 0.213 mole. Fine. Next, number of moles of CH2Cl2 dichloromethane. Okay, what is the amount given? 40 gram. Okay, dichloromethane is 85 gram molecular weight. Okay, if you calculate this, it should be 0.471 mole. Right? Now let me just do the N total. N total is basically NCHCl3 plus NCH2Cl2. Okay, if you just add them, 0.213 plus 0.471, so you will get something like 0.684. Okay, now we can find out the mole fraction of CHCl3, chloroform. Mole fraction of chloroform is going to be number of moles of chloroform CHCl3 divided by total. That's gonna be 0.213 divided by 0.684. So if you calculate this, it will come as 0.312. Up to this, at first you tell me if you understood or not. Up to this, at first you tell me if you understood this thing or not, then we will proceed. Next, if you want to find out mole fraction of dichloromethane, CH2Cl2, okay, CH2Cl2. So in this case also you can do the same thing, that is number of moles of CH2Cl2 divided by N total. So if I do it, 0.471 divided by total mole is 0.684, 0.684. So you will get something like 0.688. Okay. So now we can apply Raoult's law. Applying Raoult's law. Okay. So from here what you can do, P total is basically mole fraction of what are the component I am having, CH2Cl2 into P0 of CH2Cl2, okay, plus mole fraction of CHCl3 into P0 of CHCl3, right? Now let's put the value. What is the mole fraction it came? Let's see. Okay, 0.312 and pressure is 200. Okay, so 0.312 into 200 mm of Hg. Okay, plus here also I can get 0.688 into the pressure was 415. Okay, if you calculate this thing, you will get something 347.9 mm of Hg. Okay, that is the answer, but I am not yet done. This is only the first part. Okay, calculate the vapor pressure of the solution. Okay, that is the first part only. Please make sure, please let me just tell me once if it is clear to you or not. Pradyun is saying it's 358.35. Is it so? But in accordance to my calculation, it's coming 347.9. Can you please recheck once, my dear? Okay, by the time let me just calculate the vapor pressure as well. Sorry, vapor phase composition. Vapor phase composition for CHCl3. So that's gonna be something like pressure of CHCl3. Pressure of CHCl3 divided by total pressure. So pressure of CHCl3, how I should find out? Mole fraction of CHCl3 into P0 of CHCl3 divided by PT. Okay, so if you put it over there, should come like 0.312, 0.688 into 415 divided by total pressure is 347.9. Okay, now if I proceed with this, your answer should come something like 0.180. Okay, now y of CH2Cl2 if I do, the same thing you can put here as well, 0.312 into 200, right, divided by 347.9. Okay, so for this particular case you will get something 0.820, or in a simplified version you can do 1 minus y of CaCl3, that will also give you the answer. Okay, fine, very good. I guess it's clear to you. Let's proceed further. Just let me know if you understood this or not. Okay, next question. Here you can see, draw a switchable level diagram to express the relationship for ideal solution of A and B between the vapor pressure and mole fraction of the components at constant temperature. That's what, it's a previous year question for the board. That's what I already discussed. It's simple, the Raoult's law. Raoult's law graph itself represent the ideal gas, okay, ideal liquid solution. Okay, let's proceed further. Here you can see a few questions that is related to the solubility, reason based question. It comes often in 2 marker. That is, aquatic animals are more comfortable in cold water than in warm water. So what's the reason behind it? So basically in cold water, as temperature is less, the solubility of oxygen is more than that of the hot water, right? In hot water, temperature increases, solubility of oxygen decreases. So aquatic animal, they prefer cold water rather than that of the hot water. It's clear. Liquid ammonia bottle first cooled in ice before opening it. Okay, so why? Because of the vapor pressure. Okay, so what happens basically, the ammonia has very high vapor pressure because it's volatile, no? It's very high vapor pressure. So once you are cooling it down, so what will happen then, like the vapor pressure will decrease, right? Because we know that with temperature vapor pressure increases. So if you decrease the temperature, vapor pressure decreases. So that's the reason, if you cool down the bottle, then the sudden escape of the ammonia gas, from that actually you will get rid of it. Okay, next you can see dissolution of some solid compounds in exothermic, while that of some other is endothermic. So that is also something no, I didn't tell this. Okay, sorry. The heat, like what happens basically, the heat change during the dissolution process, it actually depends upon the different magnitude. Like also you have to take care of the hydration energy of it. Okay, so sometimes what happens, this hydration energy is more than that of the lattice energy. Okay, in that cases you can see some exothermic case. Okay, exothermic means you will see that it's liberating some heat, right? But in case the hydration energy is less than that of the lattice energy, then you can expect like the solution will be cold, it will be cooled down. Okay, that is the endothermic case. So these are few cases that must be remembered. Okay, please either you just note down in short, or we can take a screenshot out there. I guess all clear. Let's proceed further. Okay, here okay, so just let me tell you one thing. Once we are done with the, okay, what is hydration energy? Okay, hydration energy means once you are just putting down one salt, okay, the salt will be ionized, or any kind of solute, or whatever the liquid maybe you are putting, okay, that will be ionized. Means let's say if I am putting some ionic salt, those cases I am giving you an example, let's say NaCl. Okay, so Na plus Cl minus. So what will happen, the water molecule will be accumulated around it. Okay, accumulated around it means let's say I am having the Na plus, right? Na plus ion present in the water. Okay, so water molecule, the oxygen, because of the electrostatic interaction, it will create a cage, you know, like this. This type of cage formation takes place. Okay, because of the formation of this type of interaction, some amount of energy is generated. Okay, some amount of energy is generated. This is called hydration. This phenomenon is called hydration because you are putting some salt in water. Okay, in case you are putting that salt in another solvent, in any other solvent, you will call it solvation. Okay, and the energy sometimes may be liberated or sometimes may be taken, means whenever it will be cold. Okay, so that's the energy is called as hydration energy. The energy, if it is liberated, means if it is more than that of the lattice energy, it is exothermic. If it is less than that of lattice energy, then it is endothermic. Is it clear, my dear? Please tell me. Let's proceed. Here you can see one question, it is for the Raoult's law topic. Okay, one thing I just wanted to tell, my dear, once the Raoult's law will be done, then we will take some 5 to 6 minutes of break and we'll just take some water and all, and I want you people to come back and please, please, please stay with me till the end. The way you are responding, it's overwhelming, it's a festive day, but still your presence, like, it's really, I'm very grateful to you. Okay, so let's proceed with this question. Okay, so before starting the ideal non-ideal solution, after completing this, we will take a very small break. Yes, so let's proceed. The vapor pressure of pure liquids A and B are 450 and 700 mm of Hg at 350 Kelvin respectively. If the total pressure of the mixture is 600 mm, the composition of the mixture in the solution. So how I should proceed? See, P total, let me just write the Raoult's law, is basically P0 A of XA plus P0 B of XB. Now what I can do is, in case of XB, I can replace it with 1 minus XA, right? That's what I'm going to do. PA0 of 1 minus, sorry, XA plus PB0 1 minus XA. Like that I can write, and the rest of the cases, you know, you have to put the value over there. Everything is given. Okay, so here I am having the value 600, right? 600 equals to PA0 is given as 450. Mole fraction of A I have to calculate, plus PB0 is given as 700. 700 minus 700 of XA, right? It will come something like this. So if you further calculate, I am not going to the detail, you can just do here and there, you will get it. That is 0.4 you will get. So XB you can get out of there 1 minus 0.4, that's gonna be 0.6. Okay, so your answer is going to be A. I can see you people, Pradyun, Dhanush, very good, very good, very good. Okay, so let me just take a small break. You also take some little break, and please, please, please make sure that you are coming back here. Yes, thank you. Okay, so I guess you are feeling fresh now. So let's again start where we stopped. Let me check once. Okay, so now on we will start with the ideal and non-ideal solution. So basically here you can see solution that actually obeys Raoult's law and does not obeys Raoult's law. In accordance to that, you can specify the ideal and non-ideal solution. So I am expecting you student also, please just let me know if you have came back as well. Yes, please comment me below if you have came back as well, if you can see me, if I am visible, audible to you, if you also came back with your copy and pen. Let's proceed. Here you can see ideal solution is okay, but whenever it comes to the non-ideal solution that does not obey Raoult's law, it has two possibilities. Okay, one is positive deviation, another one is negative deviation. Okay, very, very important portion. Okay, so now here you can see in non-ideal solution also shows some characteristic, that is we also calls as azeotrope. That is also important. Okay, so here you can see the difference between ideal and non-ideal solution. That's going to be super important for your examination. So here in ideal solution it basically follows the Raoult's law, and in non-ideal solution it does not follow Raoult's law. Okay, delta H mix means enthalpy of the mixture is always 0, and for this case enthalpy of the mixture is not equals to 0. Delta V mix, change in volume. Okay, after mixture there will be no change in volume as such, but in this case if it is a non-ideal solution, then definitely there will be a change in volume. Okay, so now you can see AB interactions are equals to the AA interaction and BB interactions. So basically A is the two component I told you, binary mixture I have taken of two volatile liquids, so A and B. If the interaction between AA and AB, they are AA, BB and AB, okay, they are equal, then you can call them ideal solution. So most of the cases what happens, if you are taking the homologous series as example, let's say I have taken the N-hexane, N-heptane, they are homologous, the members of homologous series, right? So they will show the same type of interaction. Okay, non-ideal solution when the AB interaction is not equals to the AA and BB interaction, then those cases you can consider non-ideal. Okay. Now you can see whenever it comes to the non-ideal case, then again I told you there are two parts, one is positive deviation and one is negative deviation. So this particular thing, let me just tell, it is very much important for your board. Okay. Okay, and this particular thing concept wise this is important for your board and as well as for your KCET examination, because some MCQ type of question also they ask from this, because the examples are very important here. Okay, so here you can see AB interactions must be weaker than that of AA and BB interaction, very important point. And negative deviation, you can see AB interactions should be stronger than that of the AA and BB interaction, means after mixing the interaction will be stronger than that of the individual liquid mixture. Okay, here you can see total pressure should be greater than that of the summation of these two. Okay, here it will be less than for the negative deviation. Next, enthalpy of the mixture should be greater than 0. Greater than 0 means it is a positive value, means endothermic. Okay, here you can see it's less than 0. Less than 0 means it is exothermic, means heat will be liberated, negative deviation. Next, here you can see the example, you can see ethanol and acetone. Okay, so ethanol and acetone, just let me explain you a little bit. Ethanol itself is having very, very good hydrogen bonding, right? Very good hydrogen bonding. So AA interaction, let me just take ethanol as A and acetone as B, right? So itself ethanol is having very nice hydrogen bonding, right? And acetone, if you see, it's a polar molecule, so dipole interaction will be there, so dipole interaction will be there, van der Waals interaction will be there, right? So itself AA and BB interaction is so powerful. Now what you are doing, you are mixing ethanol and acetone. Now in between two ethanol molecule, the acetone is coming, right? So hydrogen bond will be disturbed, right? So AB interaction will be weaker. I guess it's clear to you. So this is how, maybe sometimes common example you may not face, those time what you have to do, imagine what type of interaction they may have in individual case and when they are mixed, like that. Here also you can see negative deviation. Here you can see phenol and aniline. Okay, when they are mixed, they will be having very nice hydrogen bonding. So AB interaction is stronger, right? So chloroform and acetone, here also hydrogen bonding. Okay, let's proceed further. Here you can see these are the graph of the non-ideal case, positive deviation and negative deviation. Positive deviation, you can see this green line, it indicates general ideal solution, that is the Raoult's law. Okay, and this particular curve, that blue one, you can see it is towards the positive end, towards positive, right? So from here you can tell that yes, this is basically the positive deviation of the Raoult's law, and here you can see it is towards below, means towards negative. Okay, so this is how it looks like in case of negative deviation. Very important. Okay, during lecture ask some questions. Okay, will you answer? Definitely. Whenever we will come back to the numerical problem and all, then I insist you please solve the numerical before me. Okay, that will be very much funny. Students are ahead than that of the teachers. It seems very beautiful. Okay, next let's proceed. Here comes your question, my dear. Please, I want you to answer it. Okay, so here you can see the mixture which shows positive deviation of Raoult's law. Positive deviation of Raoult's law. Positive deviation, I guess you remember the case. Okay, interaction you have to think about, that AB interaction, sorry, not this, AB interactions are weaker than that of the AA and BB interaction, right? So for this case, just check what type of interaction is the first one. Okay. Chloroethane and bromoethane, they are of similar type of compound. They will be having same type of interaction, and hence you can say this is ideal solution, right? Ethanol and acetone, yes, this is the option, right? Ethanol itself is having very strong hydrogen bonding. Acetone itself is having very nice dipolar interaction, right? When they are mixed, the AB interaction will be weaker. So that's going to be the correct one. Benzene, toluene, again the same type. Acetone and chloroform, it will show negative deviation. Can I get the PDFs? Yes, definitely you can get the PDFs later as well. Let's proceed further. Here you can see when the acetone, very important zone, again I am telling you, from this particular case the question keeps coming. These questions I am telling for the PU. As you can see, very short answer type I have written. I guess you can understand this is for the PU too. Okay, so here you can see when acetone and chloroform are mixed together, which of the following observation is correct? So definitely AB interaction becomes more than that of the AA and BB interaction. So let me just check. Okay, so option B is the correct one, I guess. Let's proceed. I can see Shakshi, very good. Yes, you can get the PDF, definitely. Let's proceed further. Here you can see ideal and non-ideal solution. I don't think that I have to tell you. Match the following type of the liquid solution with their characters. Okay, so whenever it comes to the ideal, so definitely, okay, let me just change the ink. It is definitely is going to be equals to P0A of XA, right? And this value, del H value is basically 0 and del V mix value is also 0, right? Whenever it comes to the non-ideal solution with positive deviation. So positive deviation means the value delta H value is positive, right? So delta H value is positive, delta V value is positive as well, okay, and P0A of XA is greater, right? Sorry. Okay, now for the non-ideal negative deviation, P0A of XA, it is less than 0, that is del H is negative and del V is also negative. Okay, I guess it's clear. Let's proceed further. Here you can see short answer type, give the difference between ideal and non-ideal. We already discussed, these are the point. Any two you can take, or 3 marker question as you can see, so try to write them all. Okay, let's proceed further. Here you can see differentiate between the non-ideal solution. Types of non-ideal solution means positive deviation and negative deviation. We already discussed about it. I guess you can proceed. This is a KCET question. Here you can see a mixture of phenol and aniline shows negative deviation of Raoult's law. This is due to the formation of intermolecular hydrogen bonding. Okay, intermolecular hydrogen bonding means hydrogen bonding between two different molecules, and intra means the bonding between same molecule. Okay, let's proceed. Okay, here you can see which of the following pairs will show positive deviation of the Raoult's law. So which of the following pair will show positive deviation of Raoult's law? Positive deviation means, again just a small recap. So you will see the interaction between them, A and B interaction is weaker than that of the individual interaction. So definitely option B is going to be the correct one. Benzene itself, polar solution, they will be having van der Waals interaction, and methanol will be having hydrogen bonding. So if you are putting benzene and methanol, so in between two methanol, benzene will come, so hydrogen bond will be disturbed. So positive deviation. I guess it's clear. Let's proceed. Here you can see azeotrope, very important, the definition. So what is the definition? Azeotropes which are binary mixtures having same composition in the liquids and in the vapor phase, and they together boil at the same temperature. Okay, and if they are forming an azeotropic mixture, it's basically very difficult to separate them using fractional distillation. It's very important point. Okay, I guess it's clear. Let's proceed further. Here azeotropes are of two types. One is minimum boiling azeotrope and another one is maximum boiling azeotrope. So whenever it comes about the maximum boiling azeotrope, it shows negative deviation, maximum negative deviation of Raoult's law. Whenever it comes in the form of like a maximum boiling azeotrope, it shows maximum negative deviation, remember that. And whenever it comes to the minimum boiling azeotrope, it shows positive deviation to the Raoult's law. Okay, maximum boiling azeotrope will show negative deviation, minimum boiling azeotrope will show positive deviation. Okay, examples are very important. With composition, try to write it. Okay, what is fractional distillation? Okay, fractional distillation, my dear, whenever you are having two different liquid, okay, two different liquid, they are mixed. How you will separate them? How you will separate them? You will separate them by using this method. What is this method? Two different liquid, they are having two different boiling point, right? Let's say I am taking methanol and water. Okay, so I have to separate them. How will you separate methanol from the water? Water is having boiling point around 100 degrees Celsius and methanol is having boiling point around 78 to 80 degrees Celsius, right? You are having a funnel, separatory funnel, and like fractional distillation apparatus comes actually, so you start to boil them. Okay, so when the temperature will come around 70 to 80, something will come to evaporate. What is that? That is methanol. So that particular thing, there will be some outlet, from that the gas will come, the evaporation will come, and they will get condensate, and the drop by drop methanol you will collect here. Okay, and once the 80 degrees Celsius, 85 degrees Celsius it will go, then the vapor will come, that was coming, it will stop, means all the methanol came out. right? So whatever is there in the fractional distillation apparatus, okay, because 100 degrees Celsius we yet not reached. So whatever is there still in the particular apparatus, that is basically water. So this is the way you can use fractional distillation apparatus to separate two different liquid of having two different boiling point, okay. But here when they are making the azeotrope, then the boiling point is same, okay, they boil at the same temperature, right? So that's the reason utilizing the fractional distillation method you cannot separate them. Is it clear, Shakshi? Just let me know. Let's proceed. Here you can see, give reason. Again this reason type of question, 2 marker question you can get this type of thing. Okay, next you can see an increase in temperature observed on mixing chloroform with acetone. So what basically happens, so whenever you are mixing chloroform in acetone, definitely hydrogen bond will be forming, right? So hydrogen bond, once it is formed, means it is a negative deviation. Negative deviation, why I am telling, because AB interaction will be more than that of the AA and BB interaction, okay. That means it's a negative deviation of Raoult's law. And negative deviation indicates enthalpy value less than 0, enthalpy of the mixture less than 0, and less than 0 means what? Tell me, less than 0 means it is an endothermic, okay. So that's the reason temperature will be coming out, okay, increase in temperature. Now you can see mixture of ethanol and acetone shows positive deviation of Raoult's law. That also, okay, this is ethanol and acetone. Okay, so ethanol, this is something I already told. Ethanol is having itself intermolecular hydrogen bonding, and acetone is basically having its dipole-dipole interaction. So individual interaction is more than that of the AB interaction. So that's the reason it will show the positive deviation. Okay, now pure ethyl alcohol cannot be obtained from the rectified spirit even by fractional distillation. Why? Because they form azeotropic mixture. So basically if you see the composition of the rectified spirit, it is 95.4% alcohol and rest of them are water. So these particular composition forms the azeotropic mixture. That's the reason it cannot be separated from the fractional distillation. Go and check out the answer. If it's needed, you can take a screenshot out there, or you can just make a note of it. I guess it's clear to you. Let's proceed. Here it's a diagram based question. Here you can see it is also PU2 level question only. From here usually the question didn't come since last 5-year analysis of KCET. Further we will proceed. Okay, see, for this graph answer the following question: what type of non-ideal solution shows such behavior? So I don't have to tell you, you can see that particular thing is towards the positive end. Definitely it's a positive deviation of Raoult's law. Okay, next, give example for such type of non-ideal solution. So positive deviation, I discussed methanol and that one, the last question we discussed, no? Ethanol and acetone we can take example. Okay, next, what type of azeotrope will the mixture A and B form? So maximum boiling, you can see the positive deviation, right? So positive deviation, when you will see, that is the basically minimum boiling azeotrope it will form. Okay, I guess it's clear to you. Let's proceed further. Here you can see this is a part 3. Here please whoever is diverted till now, please concentrate your mind here so that you can understand this particular portion, because that's gonna be really important for your PU2 examination as well as for your upcoming KCET. Maximum number of questions comes from this zone only. Let's proceed. Here in the colligative property, we will discuss relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, osmosis, okay, and we will discuss the abnormal molar mass as well. Okay, let's proceed. So basically this colligative property, why it comes? So let me tell you, my dear, Please remember the composition, in which case we will get the colligative property. We need a volatile solvent and non-volatile solute. What we need? Volatile solvent and non-volatile solute. Okay, so basically what happens whenever you are having a volatile solvent, so that particular solvent will try to get evaporated, right? Normal, pure state. But now you are mixing some non-volatile solute, let's say sugar, NaCl, whatever it is, they are non-volatile. So what they do, they gets accumulated on the surface of the volatile solvent. They gets accumulated on the surface of the volatile solvent, that results the decrease in vapor pressure, right? So initially when there was no non-volatile solute, then the vapor pressure was nice because volatile solvent, right? But whenever I am putting some volatile solute, non-volatile solute in it, they gets accumulated. The surface area is blocked. Evaporation takes place from the surface, right? Now the surface area is blocked. How evaporation will take place? So in general, what will happen? The vapor pressure will decrease. Okay, so that's the reason whatever the property you will get, those are called colligative property. Okay, so let's proceed. So first one is the relative lowering of the vapor pressure. So here you can see this is the formula out there. So definitely, as I told you, the vapor pressure will be lowered, right? So that is only the relative lowering of vapor pressure. So that is basically delta P by P. Delta P by P means P0. P0 is the pressure of the pure solvent minus P, the pressure that you are putting. Okay, divided by P, that is basically X of B. X of B means mole fraction of the solute. So relative lowering of vapor pressure, this entire thing is called RLVP. Okay, this entire thing is called relative lowering of vapor pressure, that is basically equals to the mole fraction of the solute. That's it. Okay, next the formula for the diluted solution. Whenever everything is same, but whenever you are just putting the mole fraction of the solute, that time Na plus Nb, right? In this case, Na is the number of moles of solvent. Dilute solution means number of moles of solute is very less than that of the solvent. As a result of this, we can neglect Nb in the denominator part, so Nb by Na, that's it. I guess it's clear. Let's proceed. Here comes a question. Okay, so I insist you people to proceed with it. Okay, what's the question? Let me just check out. Okay, the vapor pressure of water in solution having 50 gram of urea dissolved in 850 gram of water. So, okay, that's gonna be a super easy one. So, basically you have to find out the mole fraction of vapor pressure of the thing, vapor pressure of the solution, right? Yeah, because you know, whenever you are mixing urea in water, then what happens basically? Urea is not generating any pressure because it's non-volatile. So whatever the pressure coming out, it's because of the water only, right? So you can proceed it like, first you can calculate the number of moles of urea and number of moles of H2O. Okay, so how you should calculate? Number of moles of urea is 50 gram divided by 60 gram per mole. For water, if you proceed, 850 gram divided by 18. So this will come as 0.833. This will come as 0.833, and for this it will come as 47.22. Okay, now what you can do is you can find out the mole fraction of water. Mole fraction of water, how you should find it out? That is number of moles of water divided by total number of moles, means number of moles of urea plus number of moles of H2O. Okay, if you calculate, that is for water it is 47.22 divided by if you just find out the total, that is 0.833 plus 47.22, you will get almost equals to 0.9827. Got it? Now you just apply Raoult's law. Solution, that is basically equals to mole fraction of H2O into P0 of H2O, right? From here I can put the value 0.9827 into pressure is given, that is 23.8 mm of Hg. Okay, so if you come out, if you just calculate this, your answer will come as 23.39 mm of Hg. Okay, just let me know if it's clear to you. I guess it's all good. Let's proceed further. So, okay, the answer is basically 23.39, means I can take it as A. Okay, let's proceed further. Here you can see this is from the KCET. Okay, KCET 2024. Vapor pressure of a solution containing 18 gram of glucose and 178.2 gram of water. Okay, so let's calculate it in the same way. Okay, so number of moles of glucose we have to calculate, number of moles of water we have to calculate as well. So let's proceed one by one. It's given 18, right, divided by 180 gram per mole. Okay, so that will give you definitely 0.1 mole. And for the water they have given something 178.2 gram divided by 18 gram per mole. That will give you something 9.9 mole. Okay, so now mole fraction, let's calculate mole fraction of water in the same way the last one we did actually, that is 9.9 divided by 0.1 plus 9.9. So if you calculate, it will come as 0.99, right, 0.99. So now again pressure of the solution I can calculate out there. Pressure of the solution will come as mole fraction of, water, mole fraction of water. Mole fraction of water into P0 of water. Okay, so that is basically 0.99 into 760 torr. So if you calculate this, your answer will come something like 752.4 torr. Okay, so that's the answer. I can see Dhanush. Okay, very good. I guess it's clear to you. Let's proceed further. So here you can see this is the elevation in boiling point, very important. So when the same thing it will come as well. You can see when the solute is added, the vapor pressure decreases. So once the vapor pressure decreases, so what basically happened, the boiling point of the solution becomes greater than that of the pure solvent. Okay, so here you can see the graph. Initially the solvent was boiling, initially the solvent was boiling in this temperature. You can see this is the temperature TB0, right? But now after adding the solute, it is getting boiled at this temperature. Okay, you can see a change. You can see it is increasing, means elevation in the boiling point. Okay, the graph is very important. Sometimes directly graph also they ask. Okay, let's proceed. This is the formula. So delta TB is directly proportional to the molality. Okay, molality of the solution. So if you just remove the proportionality sign, there will come Kb. Okay, ebullioscopic constant. Okay, Kb. So that Kb value, most of the cases it will be given to you, and molality if you further break down, that is a given weight of the solute divided by the molecular weight of the solute into mass of the solvent overall into 1000. Okay, so this is the entire thing. So utilizing this formula we will further proceed. So here you can see elevation of boiling point was 0.52 degrees Celsius. When 6 gram of compound X was dissolved in 100 gram of water, the molecular weight of X we have to find out. Fine. So directly we can put the formula actually. So molality, if you just calculate, wait just a minute. Okay, so we know delta TB is basically m into Kb, right? So from here molality is coming something like, I am just trying to make the calculation a little easier for you, that is 0.52 degrees Celsius divided by 0.52 Kelvin kg mole inverse, right? So m will come as 1 mole per kg, right? So from there if we just put the formula out there, molality is basically equals to number of moles divided by the mass of solvent, right? From there if I want to find out n, number of moles, that will be molality into mass of solvent. Okay, that is I am taking as W1. Okay, so n will be equals to 1 mole per kg, 1 mole per kg into mass of the solvent is given as 100, right? We are taking it in kg because unit should be matched, so 0.1 kg. Okay, as a result you are getting something 0.1 mole, right? Now molecular weight you can calculate. So molecular weight you can calculate, that is number that is the mass, means given mass by number of moles, right? So from here given mass is how much? It's given as 6 gram of compound, right? 6 gram divided by here 0.1 mole. From here I am getting 60 gram per mole. Option B is the correct one. Okay, very good. Let's proceed. Okay, so here you can see next question. The boiling point of benzene is 353 point. See, these numericals are super duper important numerical for your board examination. Sometimes you can see the exact ditto same value is given. Okay, so this question probably was given in your pre-board examination. Okay, so the boiling point of benzene is 353.23 Kelvin when 1.80 gram of non-volatile, non-ionizable solute was dissolved in 90 gram of benzene. The boiling point is raised by this. Okay, calculate the molecular weight of the solute. Okay, directly we can put, but first we have to calculate the delta TB. So delta TB is basically equals to 354.11 Kelvin minus 353.23 Kelvin. Okay, so from here you will get, if you calculate 0.88. Okay, now delta TB, direct formula you can use. Delta TB is basically Kb into W2 by M2 into W1 into 1000. 1000 we don't have to proceed with, just like that we can keep. Okay, let's put the values here. So Kb is 2.53 Kelvin kg mole inverse. Okay, into 1.80 gram divided by 0. Okay, 0.88 Kelvin. We have to calculate M2. delta TB will come below, okay, into 90 gram of benzene. Directly I am taking it into kg, so 0.090 kg, right? So if you calculate this entire thing, it will come as something 57.5 gram per mole. Okay, that is the answer. I guess it's clear to you. Let's proceed further. Here you can see this particular question is for the KCET level. Okay, so here you can see 180 gram of glucose is dissolved in 1 kg of water in a vessel. The temperature at which the water boils at 1.013 bar. So, and here you can see the datas are given. So here also this is a very easy type of question. You can just proceed with the same way that we did in the last question. So what I can do is delta TB direct formula I can implement here. So delta TB is basically KB into M. So delta TB is basically KB into W2 by M2 into W1. W1 we will put in kg like the last case. Okay. So from here I can proceed. If you put the value delta TB is equals to 0.52 Kelvin kg mole inverse into 180 gram divided by 180 gram per mole into 1 kg. Okay, so if you just calculate, it's a very simple calculation. Delta TB will come as 0.52 Kelvin, right? So delta TB, it's not yet done. Delta TB is basically TB minus TB0. Okay, so let's put the value 0.52 equals to 373 point, wait, just a minute. So TB we have to calculate. So TB0 is basically at normal atmospheric temperature, atmospheric pressure. If you see, it comes as 373.15. Okay, so now TB will come as 373.15 minus plus 0.52. Okay, so you will get the answer almost equals to 373.67. Okay, so option 4 is the correct one. Okay, I guess it's clear to you. Let's proceed further. Let's proceed. I guess it's clear. Yeah. Here it comes one of the important thing, that is osmotic pressure. Okay, so here you can see the pressure that just stops the flow of solvent is called the osmotic pressure. So osmosis, I guess what is osmosis, that you know, if you are having two different concentration, like two different concentrated solution that is separated by a semi-permeable membrane, then solvent will flow from the low concentration zone to high concentration zone, right? That is the osmosis. So it has any pressure that can stop the flow of the solvent, that is called osmotic pressure. Okay, so here you can see we can use this formula, pi equals to CRT. C is basically N by V, right? N by V. So number of moles can be written as W2 by M2, and volume it came by default R into T. Okay, it's clear, I guess. Let's proceed. So here you can see two solution, if they are having same osmotic pressure, they are called isotonic solution. Here comes a very important question that I am writing as a board alert. What is reverse osmosis? Okay, what is reverse osmosis? So reverse osmosis is basically whenever like the direction of the osmosis is getting reversed, whenever the pressure is given larger than that of the osmotic pressure. Definitely you have to give some external pressure that will be more than that of your osmotic pressure. Then what will happen, the opposite, the reverse of the osmosis will take place. Means in general in osmosis what happens, from the higher concentration zone and lower concentration zone, solvent actually pass from the lower concentration zone to higher concentration zone. But in reverse osmosis, from the high concentration zone to low concentration zone, the solvent will pass, okay, through a semi-permeable membrane. This is called reverse osmosis. I guess it's clear. Let's proceed. One example for this is the desalination of the seawater. So basically what happens over there, you can see here, let's say I'm having SPM. SPM means semi-permeable membrane. For the desalination of the seawater, what we use? We can use that cellulose acetate out there. Okay, so here let's say I'm having water. Okay, that is my low concentration zone. Okay, and here I am having seawater. Okay, this is my high concentration zone. Okay, so basically here I am giving the pressure more than that of the osmotic pressure. So then what will happen, the solvent will flow from the seawater zone to water. Okay, so what will happen, the salt and the other residue from this particular case, it will be kept there only, it will be there, and the solvent will pass through the semi-permeable membrane and it will come to the water portion, means low concentration zone. So this is how desalination can be done. Okay, let's proceed further. Okay, so first question, isotonic solution have the same osmotic pressure, right? Let's proceed. Next question, here you can see pi 1, pi 2, pi 3, pi 4 are the osmotic pressures of 5% weight by volume solution of urea, fructose, sucrose and KO respectively at certain temperature. Okay, so respectively at certain temperature, the correct order of their magnitude. Okay, so what you have to check, it's all about the concentration. So weight by volume, okay, you have to check in which case you are having the maximum molecular weight and all, and then you can just proceed with. So urea is having normal 60 molecular weight, right? And fructose you are having, just a minute, fructose also you are having the normal molecular weight of 180. Okay, so here comes a small mistake actually. This particular thing, it should be KCl, okay? It's not KO, it's KCl, okay? Let's go. So urea is 60, okay? Fructose is something that is same to glucose, 180, okay? Sucrose is 342, okay? And KCl, it is 74.5. Okay, so if you just proceed in accordance to that, so concentration is basically number of moles. So number of moles will come more for which cases, whenever like if you just see this case, concentration is basically number of moles by volume, right? So number of moles is inversely proportional to the molecular weight. So concentration is also inversely proportional to the molecular weight, right? And hence pi is also inversely proportional to the molecular weight, right? So if you just arrange them, okay, if you just arrange them, so maximum molecular weight you are having for sucrose, right? So sucrose will come first. At first sucrose means pi 3. After that it will come for 180, means fructose. Fructose will be having pi 2. After that he will be having KCl. So you can get the option actually here. Okay, so option B is going to be the correct one. Okay, I guess it's clear to you. Let's proceed further. Here you can see what is semi-permeable membrane. It is a question that usually it comes in the board examination. So what is semi-permeable membrane? Give an example each for the natural and synthetic semi-permeable membrane. So here you can see semi-permeable membrane is a membrane that pass only solvent, that allows only solvent to pass through it. Okay. So next you can see the natural semi-permeable membrane is normal animal bladder, you can take the example, or cell membrane, and synthetic you can take the cellophane paper or parchment paper as an example. This is a board question. Okay, let's proceed. Here you can see explain the desalination of water, very important question. Okay, so that already I explained, you can just have a look into it. I guess you will understand this. So in case you are just making the notes, please just take the screenshot, I guess it will be helpful for you. Okay, let's proceed. Here comes the KCET question paper from the osmosis. So here you can see the swelling in feet and the ankles of an aged person due to the sitting continuously for long hours during travel is reduced by soaking the feet in warm salt. This is because of, so basically this particular condition is called as edema. Okay, but why this is happening? This is because of osmosis. So don't get diverted and don't mark it as edema. Okay, because the condition is, because the condition is called edema, and sometimes students get diverted and they mark it edema, but they are asking this is because of, what is the reason behind it? So it's osmosis. Okay. Okay, so we have ma'am, please do organic. Wait just a minute. This chapters we have studied multiple times. The main problem is organic chemistry. Okay, don't worry, we will come up with the organic session as well. So we are prioritizing the high weightage chapter actually. So a high weightage chapter, this comes very important for the board PU2 and KCET. So that's the reason we started this particular series with this chapter only. Okay. Yes, let's proceed. Here you can see the question, next question, it is also from the KCET. Okay. If 3 gram of glucose is dissolved in 60 gram of water at 15 degrees Celsius, the osmotic pressure. Okay, let's see how to proceed. So we can directly apply pi equals to N by V. Directly apply the formula. Okay. So basically we can make it something pi equals to W1 by M1. Let's take it as solute. Okay, W2 by M2 into V into R into T. W2 means weight of the solute. Okay, and M2 means molecular weight of the solute. So 3 gram into R. R value is 0.0821. Okay, into temperature. Temperature is 15 degrees Celsius. So 273.15 plus 15 will come as 288.15 Kelvin. Okay, divided by 180 gram into volume is given as 60 gram of water. So 60 gram is given. So from here 60 gram is basically equals to 60 ml. From here if I convert it to liter, that will come as 0.060 liter. Okay, so 0.060 liter that we are taking. So if you just calculate the entire thing, it will come as 6.57 atmosphere. Yes, option A is the correct one. Let's proceed further. I guess you understood it. Here you can see the last topic, that is the abnormal molecular weight. Okay, so this is caused because of the association or dissociation of the molecule. Let's say you are just adding NaCl, but after you are just putting it in the particular solution, in the particular solvent, so it will be dissociated, right? It will come as Na plus and Cl minus, right? So that is dissociation, means you are starting with the one particle, but it's getting converted to two particle. Right, so that is dissociation. And association, why? Because happens because of the hydrogen bonding, right? Because two molecule gets interacted because of the hydrogen bonding, that is association. Okay, so such molar mass that is either lower or higher than that of the expected or normal value is called the abnormal molecular mass, and it can be corrected by the Van't Hoff factor. very important thing. So you can see the formula of the I, they can be written in this 3 way. I want you to make a note of it, or just you can take a screenshot out there. Okay, so let's proceed. Here you can see this is the Van't-Hoff factor. For dissociation it is in the form of alpha. Okay, just remember the formula for your examination, that will be more than enough for you. How it comes with the derivation, if you insist me, then I will proceed with. Okay, so degree of dissociation, that is I minus 1 divided by n minus 1. I is a Van't-Hoff factor out there. Okay, for association it will be same but 1 by n. Okay, so n calculation I will show you. Okay, now let's proceed with one problem out there. So here you can see one question, that is Van't-Hoff factor of 0.1 molar BaNO3 whole twice. Solution is 2.74. Okay, the degree of dissociation you have to find out. So BaNO3 whole twice is a electrolyte, it will undergo dissociation, right? So we can use this dissociation formula. Okay, so alpha is basically, so directly just write it with alpha is basically I minus 1 divided by n minus 1. Let's put the value here. 2.74 minus 1 divided by, see, if BaNO3 whole twice, if it dissociate, you will get Ba2 plus 2NO3 minus, how many ions, count them, total 3 ions, right? So overall number, the n is the total number of particle after association or dissociation. Okay, so it is 3 minus 1, right? So if you just calculate, it will come as 0.87. Okay, and alpha will come as, if you want to find out the percentage alpha, then it will become as 87%. I guess it's clear to you. Let's proceed. Okay, here comes another question. Why do electrolytes show abnormal molecular masses? Name the factors responsible for this, that I already told you, either association or dissociation. So for this dissociation, you can see electrolytes like NaCl dissociate into ions, increase the number of particles. Okay, so that lowers the observed molecular mass. Okay, and association, you can see like acetic acid, they actually reduce the number of particle because of the hydrogen bonding. Okay, and higher molecular mass you will get. Okay, let's proceed. Here you can see, based on their nature of the compounds, assume that the compounds will undergo 100% association or dissociation. Okay, compare the Van't-Hoff factor. Okay, fine. Urea and water, let's proceed from the below. Urea and glucose, they will neither associate nor dissociate. Okay, so that's gonna be 1. Okay, acetic acid in benzene. Okay, we'll come back. First let's do the easy. So K2SO4, it will undergo dissociation, so 2K plus SO4, 2 minus, so if you count 2 and here 3, so here you will get 3. Fine, for NaCl you will get 2, right? For this case, if you want to dissociate, again you will get Fe3 plus 3Cl minus, so total number of ions are 4. So for this case you will get 4. Okay, for this case aluminium sulfate, if you do 2Al3 plus 3SO4, 2 minus, so you will get 3 plus 2, 5. Okay, now acetic acid in benzene, for this case what happens, basically acetic acid, it will undergo hydrogen bonding, right? So 2 acetic acid unit will be merged, so this particular case it will be half. Okay, ma'am, how did you find the Van't-Hoff factor for NaCl? Beta, for NaCl, just simply dissociate it, no? Na plus Cl minus. Okay, see how many ions it's coming? 2. Right? So let's proceed further. Okay, so here comes some reason based question that is for the board level. Here you can see oceans do not freeze. Ocean do not freeze. Why? Because in ocean salts are there, right? As a result of this like decrease in the freezing point, right? That takes place. So I guess it's clear. Water stops boiling when sugar is added. Okay, sugar is added. What will happen? Elevation in boiling point. Okay, you can just go through it. We already explained. The freezing point of a solvent is lowered on dissolving non-volatile solute. Okay, so why? Because vapor pressure of the solution decreases. This is the reason. You can just go through once. These are some board based question from the colligative property. Okay, let's proceed. This is a KCET question. Among the following 0.1 molar aqueous solution, which one will exhibit the lowest boiling point of elevation? So basically delta TB is I into KB into M. This is how we can proceed. So I value more means delta TB will come more. Okay, so I we have to find out. So for aluminium sulfate it will come 5. For this case it will come 2K plus, okay, 2K plus SO4 2 minus, right? So it will come 3. For NaCl it will come 2. For AlCl3 it will come Al3 plus 3Cl minus. It will come 4. So maximum will come for the aluminium sulfate. Okay, I guess it's clear to you. Let's proceed. Okay, wait. Lowest, it will exhibit lowest boiling point. So lowest boiling point will come for the sodium chloride, right? I value is lower. I guess it's clear. Let's proceed further. Here you can see Van't factor. So dimerization of the solute molecules in low dielectric constant solvent is due to definitely hydrogen bonding. Okay, so yeah, that's it. So here comes the end of the solution session. So I guess you people who kept watching the entire series, they did well, and whoever was answering, really I'm thankful to you people. And please don't forget to subscribe, like and share our videos and channel. And please make sure that you are watching the upcoming sessions on the upcoming chapters as well, so that you become the definitely you get the top 1000 rank in KCET and you get 95% plus in PU2 examination as well. So all the very best. Keep your preparation at the top and goodbye. Enjoy your festival. Thank you so much.